All right, this is one of my favorite problems with the forces between two wires. So you've got a wire down here that is fixed in place. So let's write just fixed real quick down here. And then another wire above it, and this wire is caught in some guards here, or some like guiding rails. So it actually can slide up and down, but it's like going to be kind of held in place so it can't, fall past, right? So this one can move up here. And so the question says, given a current in this wire and given a linear density of this wire, so let's write that down. Let's call this I2. We want to figure out how much current we should put in wire 2 and which direction, so that wire 2 will float a given distance d above wire 1. So in summary, basically I want to make them repel each other so that wire 2 just floats there. It's just going to hover some distance d above the bottom wire, and this rail is going to hold it in place and keep it from falling to the sides. Okay, so let me write down some extra bits of the problem, and I'll be back. Okay, so what I've added here is we're going to have a given that the current in wire 1 is 10 amps, and that the mass per length, or the linear density of wire 2, is going to be 100 grams per meter, or 0.1 grams per kilo, or 0.1 kilograms per meter, if you'd rather. And we want that wire 2 to float a distance of 10 centimeters above wire 1. So part A asks us, what direction should the current in wire 2 go? Well, what we learned in the previous video is that when the currents are in opposite directions, the forces repel each other. So we want to have the current in wire 2 be opposite of wire 1. So our answer here is to the left. And let's go ahead and draw that on our picture. All right. Now on to part B. So part B asks, what should the current in wire 2 be for it to float a distance d above wire 1? So I'll solve that equation we had before and rederive it, because you should too when you have these problems, because you want to make sure you get it right. So I should know that the magnetic force on a wire can be found using the equation of IL cross B. Remember, and this is current. We want the force on wire 2, right? So I want wire 2 from wire 1. So this is going to be the current in wire 2, the length of wire 2, the magnetic field from wire 1. But all that really is going to matter is this L term, because everything else is going to be constants and all that. And actually, it's going to be a little bit tricky here, because no one actually told us the lengths of the wire. So we're going to have to figure out how to deal with that in a little bit. So now the magnetic field generated by a wire, we can use the equation, magnetic field, we went from 1, not from 2, is going to be mu naught, which is the permeability of free space, times I1 over 2 pi d, right? So now I just take this guy and put it into here, and we'll solve for that. 2 from 1 is equal to I2 L2 mu naught I1 over 2 pi d. Put that in parentheses so we know where those all came together. And then now I just want to simplify this a little bit, and we'll say mu naught. So the question is, what should the current in wire 2 be, right? So we're going to want that I2 by itself. But, well, I guess let's simplify first before we do that. So mu naught L2 over 2 pi d times I1 I2. Okay. Oh, you guys couldn't see that last line. I'm sorry. There we go. Okay, so then let's talk about this. So what I did is I took this equation, I put it in here. So that's just going to be IL times mu naught I over 2 pi d right there. And then I just simplified, put all the constant stuff over here and my currents over here. So now I'm going to solve for I2. But the problem here now is this is still equal to whatever the force is, right? F2 on 1. So I don't know what that force is yet. So if I want something just to levitate there, just to hover, right? What does the forces need to be? I mean, I can draw a simple free body diagram. Let's do it here because I've got some space. I've got a wire, and I want to have, I know that we have a magnetic force going up, and what's the force going down? Well, it's clearly going to be gravity. So I'm going to have mg going down. So let's put that in our next line. So now I have mg is equal to, this is mass 2, right? That's the only one we're given. Is equal to mu naught L2 over 2 pi d times I1 I2, right? So we said we wanted I2. So let's go ahead and solve for that. So I'm going to take all of this other stuff and just kick it over there. So I'm going to multiply by 2 pi d, divide by mu naught L, and divide by I1. So I'm going to say M2 G times 2 pi d, and then I'm going to divide this by L2 first. I'll talk about y in a second. And then over here I'll put mu naught I1, and this is equal to I2. So now the problem we have is that no one told us the mass, right? Everyone said, they gave us like the linear density, but they never gave us the mass, and they never gave us the length. So actually aren't these two unknown? So yes, individually they're unknowns, but what was the given in the problem? The given in the problem was actually the linear density, or M2 over L. So slide that back up. So we actually know this term is lambda. Ooh, that's an ugly lambda, and lambda 2. So that's a given term. So we can write this as lambda g, let's put our 2 up front, 2 times pi d over mu naught I1, and that is equal to I2. So that's going to be my answer there, but we'll go ahead and put the numbers in and get back to you in a second. Actually, I'll just let you guys watch me write them down. So it's going to be 2 times 0.1 kilograms per meter times 10. So 0.1 and 10 are actually just going to cancel out, times pi, which is 3.14, times another 0.1. So I'm going to get 0.2 pi up top. And on the bottom, I'm going to have mu naught is going to be 4 pi times 10 to the negative 7 is mu naught. And then we said I1 was 10 amps. So we'll put a 10 down here. And I will type that in my calculator. Well, I didn't notice this at first because not always the most observant like all of you guys, and sometimes I do math the hard way. But this pi and this pi cancel. So this 2 and this 4 can turn into a 2. And I can take this 10 and turn this in from a negative 7 into a negative 6. Right? So now I'm going to have 1/2. Well, actually I can take this 0.1, right? And I can put this as another 10 down the bottom, can't I? Because I can look at this as a 1 over 10, so I can turn this into a 5 up here. So we have 1/2 times 10 to the 5, right? Because negative 5 on the bottom, so this is going to be, let's write this where you can see 1/2 times 10 to the 5. So that is going to equal to 50,000. 50,000 amps for I2. Okay, so as you can see, it's going to take a lot of current to actually make it float and to make it repel, but in principle, it's possible if you have light enough wires and big enough currents. So yeah, I hope you guys enjoyed this problem, and I'll see you guys in the next video.